today we're going to be looking at the equations for quadratic functions using two different formats. One will be what we typically see, which is the polynomial form, like 2x squared plus 5x plus 10. That's the polynomial form. This is also a quadratic equation. G of x is a quadratic equation, but it's in a different form. This is why we spend so much time, one of the reasons we spend so much time looking at the form we did for multiple transformations, so that you could start off with something as simple as x squared, look at this, and quickly, by just taking several points from your parent function, get a new sketch without having to create a table, x, y, and plug in all these points. You've learned a lot, believe it or not, in that 3-day stretch on transformations. So this transformation says, since this 2 is outside of your operation, it's post-operation, it's a vertical stretch by a factor of 2, which says multiply all of your y values by 2. So every single one of these y values will double. Then this says I'm going to shift down 3 units, the -3, because that's also outside of the operation. So 19 becomes 18 when it's doubled, Ken. And then when you subtract 3, you get 15. All right. Then the only thing going on with your input is happening right inside this parentheses before you even apply the operation of squaring. So that means it's pre-operation, and pre-operation, you're lying down on that stretcher. It's a horizontal shift. It's always not what you think. Just think about making that a 0. You'd have to add 1. You'd have to have x be 1. So you add 1 to all of your x values. So this -3 becomes a -2. So those are the 3 different transformations. This is your final point. You do the same to all of the x values, Ken. You add 1 to all of them. Nope, that's the y value. That's the vertical stretch. Okay. So all the x values have one thing happening to them. Look, if you look, you compare these 7 x values to the new points, the transform points. Only thing that's happened to x is 1's been added to the x value. That's it. Y, to get these y values, you've had 2 things occur. You had the doubling, and then you had the shift down. So you double all of these, and you subtract 3. So these would be like, if these points were A, B, C, D, E, F, G, these would be the coordinates of the transform points. And that's what Nick was talking about in his explanation below. Given any point on f of x, here's 7 of them. Given any point of f of x, you can transform the coordinates by looking at these transformations and applying it to the original coordinates. So that's what he was talking about. You say, oh yeah, this is what's happening, and you can do it in multiple steps. I just did them all at once because the answers were here. You could have done each transformation one at a time if you wanted. So it's a vertical stretch by a factor of 2, shift to the right by 1 unit, and then a vertical shift down 3 units. Those are the 3 transformations that have occurred. Now you can now look at this formula. That's the really nice thing about a quadratic equation in this form. Here's your vertex, 1, 3. That's the vertex of G. 1, -3. And 1, -3 is the vertex. And can you see it up there without too much inspection? Can you see it in this formula, the 1 and the -3? Because when you look at this, you know it's shifting to the right one. So you don't call it -1, it's 1. So notice it's 1 here. And then all your y values go down 3. So here was your original vertex at 0, 0. So if I just follow my shifts, I go to the right one and down 3. Why didn't I have to worry about the multiplication of 2 to get my new vertex? Because if my original vertex here is 0, multiplying it by any number is not going to change it. So all I have to do is move right 1 and down 3. There's my new vertex. You can also pluck them right off of here. Look, that's 1. And then you take this whole thing, and that's your y value. So when you have a quadratic equation in this form, boom, you get your vertex immediately, which is a very important point. Sure. Yes, good question. That's where I would. That's right. If this exactly where I was going next, Rose, I actually paid Rose to ask that question. If this equation said 2 times x plus 1 squared minus 3, then this would be shifting to the left 1. So my vertex here would be -1, -3, right? Yeah, that's all you have to do, -1, -3. The reason is because the form of the vertex form of the equation will always be in the form of x take away some number. So if you see x plus a number and you have to write that addition as a subtraction, then do you agree, Rose, I could write this as x take away a -1? And there's your -1. Yeah. Yeah. It's actually nicer to actually think about knowing what you know about transformations versus trying to think of it that way. Yeah. All right. And then let's see what else we have to talk about. The role, so I think the answer that table 4 gave here was the role of the x coordinate, not the line. Because the x, I agree that the x coordinate of 0 is part of the vertex of this original function, and x being 1 is part of the vertex of the transform function. But it's asking about the role of the vertical line in each one of these. So let's take a look at that. The vertical line x equals 0 is more famously known as the y-axis. So what is the role of the y-axis with my parent function, which is this black? We've got so much going on here, but just our parent function. What's the role of the y-axis? It separates it. How does it separate it? In halves, mirror images of each other, right? And so that's what makes it the line of symmetry. That's what we call that. X equals.
Are we just talking about the graph-wise or parabola-wise?
Okay, so let me clarify that. The vertex is a point. It has 2 coordinates. The x value of the vertex is the equation for your line of symmetry.
Oh, really?
Okay, so notice the x value right here is the vertex right here is 0, 0. And our line of symmetry is x equals 0, goes right through x equals 0. So this is the line of symmetry for our parent function, for f. We say that f has even symmetry because if we go to the right and left of 0, 0, we go in opposite equal distances from 0, we come up to the same height above the x-axis. F of the opposite of x equals f of x. That's even symmetry. Now, if we look at our pink parabola, our blue parabola here, and sort of what table 4 was saying was at the right idea, they're looking at the x coordinate, the value of the x coordinate for the vertex, which is 1. Now, if we create a line, x equals 1, that's this vertical line that goes straight through that vertex. And that is now the line of symmetry for our transform function. So this plays the role of the line of symmetry for the transform function g, for g. So if you know your vertex, you know your line of symmetry because it goes straight down through your vertex, because your vertex is where you can fold over your parabola, okay? And have the points on one side meet their corresponding points on the other side. That's where the symmetry occurs. Okay, so let's take a look at the demo today. So the standard form of a quadratic function, okay, this is the standard form. it looks like this. It's really what we just looked at, but in a more general form without specific numbers for A, H, and K. Okay. This is what your book calls it. Just so you know, if I ever, use this term, it's because this is what I'm used to using. I often refer to the standard form as the vertex form, just because that's what I was used to calling this, the vertex form of a quadratic. Because when I look at that, I immediately know H comma K is my vertex. So I'm just used to calling it that. I'll try to refer to it as often as possible as the standard form, only because that's how your book refers to it, and I want to be consistent with your book. But if you hear me say vertex form, it's the same. All right, let me come back to this beginning. This form right here is the general form, what you're used to seeing, ax squared plus bx plus c equals f of x. But really, general form, who's going to remember that? It's really the polynomial form. That's it as written as a polynomial. So another way to think about this is it's a polynomial. So remember, your polynomials have all real numbers for their domains. All of the exponents are nice. They're whole numbers, 0, 1, 2, 3, 4. No negative exponents and no fractions. So polynomials are kind of nice functions. They're easy to graph for the most part compared to other functions we look at. All right, except for straight lines, which are pretty easy. All right, so let's see what we can tell about a parabola from looking at the standard form. Tell right away from looking at the parabola in this form, one of the most important things, not the only important thing, is we get the vertex right away. It identifies the vertex, HK. The leading coefficient is A. Notice the leading coefficient right here is A. The leading coefficient is the coefficient of your x squared term. So if you were to multiply this all out, your first term in here would be x squared, and then it would be ax squared. Now, what's really an interesting point to notice is whether you have this form or you have the polynomial form like this. Notice, if they were going to give you these two forms, and the A in the polynomial form and the A in the vertex or standard form were different, they'd have to use a different letter here because people would get totally screwed up. So what that tells you is, if you know the leading coefficient in either one of these forms, if I gave you a quadratic equation in this form and you can identify A, guess what? That's the same A right here. The value of A is the same in both of these forms. So you can easily move from one part of, from a polynomial to here by substituting the same value of A. We'll have a chance to do that in a minute. A also tells us something about how the parabola opens. If A is positive, the value for A is positive, the parabola opens. It's just really a review of 096 stuff, up, right? It's a happy parabola, right? It opens upward. And if A is negative, well, negative people tend to be sad, opens downward. All right. Now, this is the other thing to think about is, what about the value for A, regardless of the sign? So we can sort of investigate this question by just looking at a couple of graphs. So it says large values of A. So let's look at large values of A. Where is it? Must be hiding under here. Let's take a look at A being small now. Zoom 6. There's x squared. There's half x squared, a quarter x squared. So what's happening to it? It's getting, so it's either a horizontal stretch or it's a vertical shrink, right? One or the other. So let's keep making, what's going to happen to, now this, we got this really bold parabola there. I'm going to make A even smaller, really small. What's happening as A gets really close to 0? What's going to happen to that parabola? What's it going to get close to being, huh? Yeah, it's going to be very close to becoming a horizontal line, but it's not x equals 0. What is it, Nick? Y equals 0. So let's make it really small, like 0.01 x squared. Let's try that. Let's see. We'll take all these off so we're not, our picture isn't too fuzzy. So let's put in 0.01 x squared. And now let's take a look. Zoom 6. I wonder if we'll even, let's see what it looks like. There's x squared. Whoa, look at that. It looks pretty close to being a straight line because it's like just, it's like its curve is like minuscule above the x-axis. Right? So those are just things that you can sort of like, as you look at each of your graphs, each of your equations, look at A. And don't just think about whether A is like going to open the parabola up or down, but think about how narrow it will be if A is a fairly large number in absolute value, or if it's a really small number, it's going to be really wide. Liam? Yep. Well, whatever x you use in any equation can be put into the other, because x is a variable, but a, b, and c will be constant numbers. So this is the only one that directly transfers. B has no place in here, and C has no place in here. No, and that's one of the big errors that students make. C is the y-intercept, right? When x is 0, there's your y-intercept. That k is not your y-intercept. It's the y-coordinate of your vertex. The only time, Nick, these are the same as with when you have 0, 0. Okay? But that student in my first class thought that was what happened, that C became K. So A is the only direct equivalency. All right, so we've already answered this. When the leading coefficient gets close to 0, our parabola gets closer and closer to becoming the horizontal line known as the x-axis here. All right, so it could be any line depending on the value. Any horizontal line. Okay, so here we go. So how do we transform from the polynomial form to this standard form? So let's see. We just said the A in both of these is the same. So if we're going to go from this form to this form, we need to have something, some formula in terms of A, B, and C that will give me the vertex. And you actually have worked with this formula over and over again as part of your quadratic, but never probably saw the relationship to your quadratic formula. If you have this form, so let's make up something. F of x equals x squared minus 4x plus 3. So there's my polynomial form, or what we called earlier in the preview exercise, the general form. All right. If I want to convert this to the form that has the vertex, notice here, A is 1, so it's still going to be a 1 out there. You don't have to put it in. So now what we have to do is we have to find h and k. And you can find h and k from the polynomial form because, yep. So in this quadratic form that you're used to working with over and over again for your quadratic formula, A is 1, B is -4. And C, even though we don't need it, we might as well take a look. C is 3, but we don't need it. The vertex, the x-coordinate of the vertex, the x-coordinate of our vertex, which we're referring to as h here, is the opposite of B over 2a. That should sound very familiar to you, right? Because what does your quadratic formula look like? The opposite of B plus or minus something over 2a. B squared minus 4ac. So notice that 2a is the denominator for each of those pieces in the top. So you could rewrite that as -b over 2a plus or minus that junk. So this says, what does the quadratic formula give us? The quadratic formula gives us the values for x, if there are any, where y is 0. We always set our quadratic equation equal to 0. So think about it. Your x-intercepts, your vertex is halfway between your two x-intercepts. And look, here's where you begin. Here's the x value of your vertex. So here's your vertex. To get to one x-intercept, you add a value. To get to your other x-intercept, you subtract the same value. So if you tear apart that quadratic formula, there's your formula for the vertex. So you never have to memorize it because I know you know the quadratic formula. So let's find the vertex. Let's find h here from this polynomial form. The opposite of b is 4. So, and 2a is 2, so it's a 2. So immediately I can go in here and put a 2 in for h. And now I just have to figure out k. Okay, couple of little points here from errors from past students. For whatever reason, students get so excited about finding the vertex, they forget to square it. So make a little note there to make sure you square it. This is a quadratic. Okay, the other common error we already talked about. This number here, 3, is not the value of k. This is the value of your y-intercept. So now let's find the y vertex, the y value of our vertex, which we call k. So if x is 2, how do I find y? Plug it in, right? We plug it back in here, f of 2, and we find y. So that's what this means, f of whatever the value, the x value is of your vertex. You have to find h first, yep. 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 So 4 take away 8 is -4 plus 3 is -1. So now I have everything I need. There I am, right here. So be careful. What's my vertex going to be? The value of my vertex? 2, -1. That's my vertex. And if you solve this equation for 0, you'll find that your 2 x-intercepts are y and 3. So remember, this is 2. You're going to add and subtract 1. So all this stuff in the discriminant and all that comes out to be 1 when you solve this quadratic equation for 0. Yep, Catherine? How I find k? Okay. Well, how I find the y value for anything is to plug in x and solve for y, right? It's just now called function notation, right? So if I take this equation right here and make it look more familiar like this to you, and I come along and tell you that x is 2, and I want to find the y value, I just put 2 in for x. And remember, y is f of 2. I'm finding the partner for 2 by plugging it back into the function. Okay? Is in this case, because I'm trying to find the value for y, x is 2. But I could find the value for any point on this parabola, Mahendra, by just putting a value for x in. Like if I put 1 in, I know 1 is one of my x-intercepts because I've already done it in my head. 1 square is 1, take away 4 is -3, plus 3 is a 0. 1, 0 is an x-intercept. If I put a 3 in here, 3 squared minus 12 is -3, plus 3 is 0. So 1, 0, and 3, 0 would be my x-intercepts, which you can find by either factoring this thing or putting it into the quadratic formula, which is, you know, everything turns out really nicely when you do that in the quadratic formula. Anytime you can factor something, the quadratic formula comes out looking pretty nice because you have rational answers for your x-intercepts. All right, now all this stuff I told you about where this formula -b over 2a, trying to help you see where that comes from in terms of the graph. I'm never going to ask you about that. I just think sometimes when these formulas come out of what seems to be the clear blue, where do they come from? Might help you just sort of remember and put all this stuff together. All right, so the other thing that's really important here is what I was just saying, that probably, you know, maybe you heard some of it, maybe you didn't, has to do with How do I know when I'm looking at an equation like this, whether I have any x-intercepts at all? And whether they're rational numbers or irrational numbers? Make my y 0, yep. And would I have to go through the whole quadratic formula to determine that, or is there just some simple thing I could look at? Maybe not so simple, but some part of the quadratic formula that helps me decide or differentiate or discriminate. Hopefully that word helps. The negative b over 2a just tells me the x part of my vertex. So there's not much left in that quadratic formula. We know the minus b over 2a tells us the x value of the vertex. What's going to help us, huh? The discriminant, right? That's why I said help me discriminate. If we look at, let's take a look at this formula, right? This equation right here. Whoops, let me put in a blank page. So if we look at this, y equals x squared minus 4x plus 3, and you set it equal to 0, then when you solve this equation for x, you're finding your x-intercepts. You know that, okay? If I want to know ahead of time before I start graphing this parabola, if it's going to go through the x-axis, and if so, is it going to go through the x-axis once or twice or not at all? Because remember, your axes are real number lines. So if I'm going to be going through my x-axis, then when I solve for x, I have to get a real number. Not always. X squared only has 1, right? And any horizontal shift of that only has 1. And that happens when this expression right here, Ramsey's, is a perfect square, like x minus 1 quantity square. There's only one value of x that makes that 0, and it's when x is 1. If you had something like this, x minus 2 quantity square, then it would be 2, 0. But if you multiply this all out, you don't know necessarily when you look at that, that's a perfect square. But if you tried factoring that, you'd get x minus 2, x minus 2. And that's what tells you it only has one x-intercept. All right, but without doing all that, how could you tell whether it has one x-intercept, 2, or 0? That's the discriminant, as Taylor mentioned. And the discriminant is just the piece that sits under the radical sign. This red piece right here, that gives you a whole lot of information. So if I use this on this equation, I get negative 4 squared minus 4 times a times c. And I know that that's going to be sitting under a radical. So that's 16 minus 12. That's 4. Hey, baby, give me square root of 4 anytime. I can do that in my head. It's 2. Anytime this is a positive number, then I have 2 x-intercepts. Anytime b squared minus 4ac is positive, I have 2 real number intercepts, x-intercepts. If that number is a perfect square, I have rational numbers for my x-intercepts. And I could have factored the original equation pretty easily, usually. If it isn't a perfect square, then you have irrational, but you can estimate those with your calculator. If this is less than 0, what's the story? Morning glory. If it's less than 0. Well, no. All right, so Jasper said imaginary, complex imaginary roots, which aren't on the number line. So it doesn't say it's going down. You could have something like this. F of x, you could say f of x equals any vertical shift of x squared, like plus 5. It goes like that, right? That has no x-intercepts. That are real numbers, it has complex imaginary x-intercepts. We'll get to those in a couple of days. And when b squared minus 4ac equals 0, that's when you have just one x-intercept. And that only happens when you have a perfect square to begin with. Perfect square trinomial. Or if it's in this form, you can tell it's a perfect square. If it's in factored form, you can tell it's a perfect square. That's probably a little more information than you need to have, but it's nice to try to put everything that we've been sort of talking about with quadratics together now. So let's work with this on the next problem. Okay, number 2. We finished, excuse me, number 3. We finished number 2, right? Yeah. All right, so number 3 says, all right, here's where you start to put all this together. Here's the polynomial form right here. It's written out as a polynomial or a general form, and we want to turn it into the standard form. So we want to turn this into a times the quantity x minus h squared plus k. So the only thing right now I know is that a is equal to -1. That's all I know. So let's put it in the vertex form, or this, what they call the standard form. So I can put the -1 in there right away. And again, little reminder, don't forget your square.
I have a question about that. In the first activity, we kind of like disregarded
No,
transformation.
no, you didn't. You didn't disregard it because you knew to draw a parabola. The square tells you it's a parabola.
So that's all that square really.
Yeah, it tells you the shape of the graph. Yeah. It's not all, it's everything, really.
I mean, I was thinking, like, with the values.
Yeah. Okay. How are we going to find h? Right, negative b over 2a. So let's go up here to our formula. B is 4, so I get -4. A is -1. 2 times -1. So h is 2. Woohoo! We're almost done. H is 2. I square that, and now I need k. The opposite of b up here, Jasper, is 4. So that becomes a -4. A is a -1. 2 times -1 is -2. -4 divided by -2 is 2. Any other questions on that? All right, so here's where the colossal mistake happens is, and we've already talked about this, the 1 from up here doesn't scoot and become the k value. They're 2 different roles. This is the y-intercept, and this is the partner of my vertex, right? The y value of my vertex. So to find the y value, I plug 2 in up here, f of 2. And I get -1 times 2 take away 2 squared plus k. Oh, wait a minute. I go back to my original formula. That's not going to help me. X minus 2 squared plus k. So I go back to my original formula and plug in 2. So -1 times 2 squared plus 4 times 2 plus 1. So that equals -4 plus 8 plus 1, which is 5. So that means I can replace a with a 5. And that's the equivalent form right there. Oh, I forgot to put that. Forgot to record that. Oh no. Well, hopefully whoever's going to watch this can tell from looking at the notes. All right, so what I've been saying over and over to you when we've been dealing with straight lines is you find the slope, you get part of your equation done. Let's say the slope is 2 and you have y equals 2x plus b. How do we find b? We take any point off the straight line and plug it in and solve for b. And I said we're going to be using this strategy over and over again for all the different functions we look at, and that's happening next in number 4. So we're working backwards. We're usually given an equation and asked to graph it. Here's a graph, and now we want to come up with the equation. So which form do you think you're going to use? The vertex form, the standard form, or the polynomial form, the general form? Standard, which is the vertex form. And the reason why we're doing that and not the polynomial form, Ken, I think it was Ken that said polynomials. Is that right? Oh, okay. Okay, someone said polynomial. The reason why I'm going to use the standard form, or what we've been calling the vertex form, is look right here. I got the vertex. Woohoo! Sitting right there looking at me, 3, 5. So that means automatically I can fill in the h is 3, and I don't forget to square it, and my k is 5. Look at that. Holy schmoly, guacamole. I've got almost the entire equation done. Just like when you are trying to find the equation for a straight line and someone tells you the slope. You only got one number left to fill in. So you take a point that lies on the line and plug it in. Here we have everything solved in this function except for the value of a. All I need is a little birdie to come along and tell me one point that's on that parabola other than the vertex, because I've already used that. Do I know any other point on that parabola? I know the y-intercept, and I know the point symmetric to the y-intercept, right? I know the point symmetric to it. I could use either one of those to plug in for x and y and solve for a. Which one I use, it doesn't matter. However, anytime one of your variables is 0, that makes your arithmetic so much easier. So I'm going to take the 23, and I'm going to put it as my output. F of 0 is 23, and x is 0. So now I solve for a, and I'm done. I got my equation. 23 equals a times negative 3 squared plus 5. 23 equals 9a plus 5. 18 equals 9a. A is 2. So now I can come up here and replace a with 2, and I am done. So just like you do with your lines, you take a point, throw it into your equation, and solve for that final piece of the puzzle. Okay, so you, I think, have a lot of class activities which you're not going to be able to get through. However, I suggest please do them. In particular, make sure you do this class activity is very much what we just did. This maximizing area, we want to put big stars around there. Why? Why, Linda? Why? Why are you making us do that? Anybody have an idea? Yeah, to save money? Oh yeah, the farmer. Okay. You will see something like this again. Maybe a really big exam. No, it's not on the project. Okay.